Hello, this is Professor Kuehn, and welcome back to my lectures on electricity, magnetism, and light. You might recall in my last lecture, we employed Huygens' principle to demonstrate that the law of reflection follows naturally from the wave theory of light. Now, in this chapter, chapter 16 in A Student's Guide Through the Great Physics texts, what we're going to do is look at how the law of refraction, or Snell's law as it is sometimes called, also follows from the wave theory of light. But before we do that, and before Huygens does that, he does a slight digression on the nature of materials and the relationship between the material itself and the propagation of light. Here's the basic puzzle that he's going to be trying to address. He's going to say, well, we know that light travels like a wave, and the medium through which it travels is the ether. That's what he had demonstrated back in chapter 13 and 14. But the question is, why is it that some materials are transparent, like glass and diamond, transparent gemstones? Why is it that some materials are transparent and yet others are opaque? This is a puzzling question that he's going to try to answer. And in trying to answer this, he's going to be led inevitably to the atomic structure of matter, which he's going to speculate about. So we are right now on page about 189 in A Student's Guide to the Great Physics texts. This is chapter 3 of Huygens' book called his Treatise on Light, and here he's going to talk about refraction. Now, one of the things that he's going to do on page 189 and page 190 is speculate about the way that light travels through substances. After all, remember, the idea is that ether fills all of space, and that is how light travels through space. But how does light travel through transparent materials like glass? And what Huygens is going to do is present three possible theories for how light travels through glass. So at the top of page 190, he describes his first theory. According to this first theory, he says, first then, if the ethereal matter cannot penetrate transparent bodies at all, their own particles would be able to communicate successively the movement of the waves. So according to this first theory of propagation of light, so question, how does light propagate through materials? That's the question he's trying to address. And the first answer, answer one, we'd say that the motion of particles, so the waves travel via the motion of the particles of the medium itself. So you might imagine if we have a material, let's say a glass material. I'm going to sketch a block of glass. And then on the outside, so here is glass. And then out here is the ether. Remember, his idea is that this entire region of air is also filled with this other medium, this ether, right? And he's understanding the waves of light being compressions and expansions of this ether. So you might imagine these sort of waves of compression and expansion of the ether that are incident upon the glass. And according to this first hypothesis, he says if ether does not penetrate the glass, well then how does light go through the glass? Well, the glass is comprised of these molecules or atoms or some small parcels of glass. And perhaps when the waves of ether strike it, well, that causes waves to travel through the glass itself. So it's not that the ether is penetrating into the glass, but rather the glass molecules or particles or atoms or whatever you might call them are themselves vibrating. That causes the wave to travel through like that. And then by the time it gets to the other side, these molecules of glass are bouncing then, pushing against the ether that's on the other side of the glass, causing these waves to pick up on the other side and go through. So that's his first theory. Now, why does he say this is a plausible theory? Well, he says, first of all, one reason why you might think it's not plausible is because glass seems to be a solid substance. So how could the particles of the glass move? After all, it seems like a block of glass moves as a whole, not the individual parts of it by themselves. Whereas something like a fluid like water, the parts of it can move among themselves, so you can mix water up. Glass you can't really mix up. The parts of glass don't redistribute themselves. So that's a puzzle here. And he says that puzzle is in fact illusory. He says, and this is kind of the atomic theory of matter that he's picking up on, is that these little pieces of glass are separated by spaces. It's not continuous. So the glass particles, this might seem obvious to you coming from an atomistic viewpoint, but this is a novel idea here. The glass particles are separate and separated by spaces. And because they're separated by spaces, they can move and vibrate. So you might have one particle, this is a zoomed up view. So if you think about here, let's zoom up on a region of the glass. These glass particles are spaced from each other, so when this one moves, it can then push against this one, which then moves, and so on. And he provides evidence of this in saying that when you have a magnet, this is where he says about the middle of the first full paragraph on page 190, he says, for primarily their rarity, or the spacing between the pieces of glass, their rarity is shown by the facility with which there passes through them the matter of the vortices of the magnet, and that which causes gravity. What is he getting at here? He's saying we know that there are spaces even in glass because if you hold a magnet over here, well, the magnetic effect penetrates and can attract another magnet. So if you have two magnets, they can attract one another or repel one another, of course, depending on whether you have the north or south faces facing each other. So if you think of this magnetic force as being communicated via some kind of vortices or fluid or something like that, that must be penetrating through the glass. And for it to penetrate through the glass, there must be spaces in the glass. And likewise, gravity penetrates through glass. It's not like if you take the Earth right here, so suppose here's the Earth, whoops, that's a bad drawing, and then you take a piece of glass right here, and then you take an apple right here. The apple normally falls to the Earth, but if you put a piece of glass between them, it's not like the glass can block the gravity to prevent the apple from falling. Whatever gravitational attraction is felt by the apple toward the Earth, which Huygens is suspecting is mediated by some kind of material that penetrates the glass, you might argue about this, but that's what he's suspecting, then there must once again be holes or pores or spaces within the glass. And so this supports his idea that even if the ether cannot penetrate the glass, at least the atoms or molecules of the glass can move and vibrate and carry these vibrations. Okay, that is his first hypothesis. Another hypothesis, answer 2, is that perhaps the ether itself, the ether particles, can penetrate the glass, and the ether waves, that's the waves of light, thus, or in this way, travel through the glass. Okay, so this is the second idea that he has. This, by the way, is at the top of page 191. If we jump ahead here, he says the second mode then of explaining transparency, and one which appears more probably true, is by saying that the waves of light are carried on in the ethereal matter, which continuously occupies the interstices or pores of transparent bodies. Okay, so I'm going to draw a picture right here. Now, according to this theory, once again, if you have a piece of glass right here, sure enough, you've got little pieces, you've got little atoms of glass in here. And then out on the outside, you've got these particles of ether. And when you create waves of light, there's compressions of the ether. But now the ether itself penetrates into the glass. And it's not the little pieces of glass that are vibrating, rather it is the ether itself that's interpenetrating within the glass that's supporting these waves that travel through the glass, and then these once again pick up on the other side, and these waves then travel through like this. So again, according to this theory, the waves are supported by the ether alone, which penetrates, and I guess I already said this, but I'll say it again, which penetrates the glass. By the way, why would he believe that ether can penetrate the glass? That's an interesting idea, and he argues that the ether can penetrate for a couple of reasons. The first one, you might recall, he harkens back to the old experiments of Torricelli, where if you put a sounding body such as a bell inside of a glass jar, if you were to pump the air out of the glass jar, you can no longer hear the bell, and yet you can still see the bell. Therefore, when you pump the air out, the ether must still be inside of there. How could it still be inside of there? Well, he would argue because the ether particles actually can penetrate the glass, leak in from the outside, and fill the glass even when you try to pump them out. Another explanation he provides, and this is, we'll go back a page, back onto page 190, and so this is the bottom, the last paragraph on page 190, and the top of page 191, he carries out a thought experiment that runs something like this. Imagine that you have a glass sphere, like this. And I'm going to draw it with some thickness, so this is a glass sphere. And if you take this glass sphere and you try to shake it back and forth, it has some inertia. That is, it's hard to change its direction. When you shake it back and forth, the difficulty with which it takes to slow it down and speed it up in the opposite direction depends on the mass of the glass, the how much it weighs. So if you take this sphere of glass and it's empty and shake it back and forth, it's easy to shake it back and forth. But if you were to take this glass sphere and you were to fill it with water, like this, the water, of course, has weight, right? And so now if you try to shake that glass sphere back and forth, it's harder to turn around. It's heavier, so it's harder to stop it, reverse it, and make it go in the other direction. In other words, it has more inertia by virtue of having water confined within the glass sphere. And the reason, importantly, is that the water cannot penetrate the glass to get out of it. It's contained within the glass, so it adds to the inertia of the glass sphere, making it difficult to turn back and forth. Now, what if you have a glass sphere like this, and you try to shake it back and forth when it's empty? Well, if it's empty, but it is filled with ether, let's put little hypothetical ether particles in here. If the ether could not penetrate through the glass, it was trapped in the glass, much like the water is trapped in that glass sphere, then the weight of the ether should add to the inertia and should make it harder to shake back and forth. It should make it harder to turn it around and shake it back and forth if it was trapped. So if the ether is trapped, it would add to the inertia, or increase the inertia of the sphere. And you could test whether, in fact, this ether was trapped by taking the exact same glass, and instead of having it in a hollow spherical shape, you were to take the same mass of glass and melt it and reform it into a solid block of glass, like this, and try to shake that back and forth. And notice now here, there wouldn't be ether trapped inside in the same way that it had been here. So this should be easier to shake back and forth if, in fact, the ether could not penetrate the glass and it was trapped in this larger hollow glass sphere. As it ends up, it's just as easy to shake the hollow sphere and the glass block back and forth. Therefore, if there's ether inside of here, it must not be trapped. It implies that the ether must be able to penetrate. Must penetrate the glass so that it does not contribute to the inertia. so that it doesn't contribute to the inertia. So this is another argument that he provides. It's a subtle argument, but it's an argument that he provides on the bottom of page 190 and top of page 191 that argues that the ether can readily penetrate even seemingly solid materials. Okay, so that is his second answer, his second possibility. The third possibility, and this is something that he mentions, I suppose, on the bottom of page 191. I'm just about out of space here, so I'm just going to tell you about this. Maybe I'll squeeze it in at the bottom here. Is really a combination of the previous two. And this is the one that he tends to be more partial to. He says the third and last mode in which transparency might be conceived, again, these are hypotheses, which is by supposing that the movement of the waves of light is transmitted indifferently both in the particles of the ethereal matter, which occupy the interstices or the holes within the body, and in the particles which compose the body, so that the movement passes from one to the other. So here you have the idea that the ether is outside of the glass and inside of the glass, and these waves that are passing into the glass are supported both by the vibrations of the glass molecules themselves and by the vibrations of the ether that is within the glass. Why is he partial to this? Well, he thinks that it can possibly explain why it is that certain materials are transparent and certain are opaque. So he mentions this at the first, second, third, fourth full paragraph on page 192. He says, whence then, one will say, does their opacity come? Is it because the particles which compose them are soft? That is to say, these particles being composed of others that are smaller are capable of changing their figure, and so on. So he's bringing up this issue of why is it that that certain materials like glass are transparent and others are opaque, like silver or copper or gold. And he's going to suggest that whereas glass is comprised of small particles that are small hard particles that readily vibrate so as to transmit these vibrations through, other materials such as silver and gold, in addition to small hard particles, they also have larger soft particles that tend to absorb the vibrations traveling through them so that they do not propagate through the material. So again, all of this is very much speculation on his part, but the point I want to make to you is that when you're asking questions about why light travels through materials and does not travel through other materials, you are very quickly drawn into speculations about the atomic structure of that material. And remember, this is in the 1690s that he's thinking about this, and as physics, as the science of nature, the science of physics progresses throughout the years, there is going to be increasing interest in trying to answer these exact kind of questions that Huygens is raising here. And really until we have this atomic theory of matter comprised of protons and electrons and neutrons and how each of these interact with waves, until we have a proper theory of protons, electrons, and neutrons, it is going to be very difficult to understand why some materials are opaque and others are transparent. This is something that we address in some detail in my Physics 302 Advanced Electricity and Magnetism course. So I'll put it off until we get to that course. Now, having gone through this briefly, page 190 through 192, now what Huygens turns to is the question of how can the wave theory explain the law of refraction? And so on page 193, he reminds us of what the law of refraction is. So if you have a ray of light coming in along line AB in figure 16.1, it strikes a glass block, the surface of which is located at FG. Then the ray of light will bend, it will undergo refraction, and it will travel in the direction BC. So he's reminding us what the law of refraction is, and then in the following figure, which is on page 194, he's going to explain this in terms of the wave theory of light. And I'll come back to this in my next lecture.